Greetings to everyone. My name is Chinmay Vinay Dandavate. I am a student of MSc Statistics Semester 2 at the Institute of Science Nagpur, which is an autonomous college under the government of Maharashtra. And the topic which I have been allotted for the seminar of this paper based on the stochastic processes is pure depth process. So before I actually come to my topic, I would like to share this quote which might superficially seem very much irrelevant. It is from the Srimad Bhagavad Gita, which states that change is the law of the nature. As regards the topic of pure depth process, or for that matter, this entire paper of stochastic processes, or to some extent the transportation theory, all these processes stand on the fundamental concept of change. Almost everything in this world which has evolved so far, right from the smartphones which we use as compared to the basic telephones, right from the sophisticated houses where we live, the clothes which we are wearing, the food which we are eating, the society in which we live, everything is an outcome or is a product of change. And not just this synthetic changes, almost every evolution in the nature and in the entire cosmos for that matter is a product or is a manifestation of change. The whole world, the whole cosmos is functioning on this fundamental of change. But change in itself can be classified into two broad types: physical changes and chemical changes. And both of them have their respective characteristics and properties. Physical changes are those changes where no new substances are formed. The mass of substance doesn't alter after the change has occurred. It's a temporary change and is easily reversible. Whereas chemical change has a new substance formed in that process. The mass of substance alters after the change has occurred. The change usually is a permanent change and essentially is irreversible. That is, it can't be nullified or it can't be brought back to its original state. Now, as regards this topic of pure death process, chemical change is the type of change which resembles a lot to this pure death process. So, what can be few examples of chemical changes? So, here I am listing few of those many examples of chemical changes. Firstly, the radioactive decay. Radioactive materials, they lose their radioactivity over time due to decay. This process can be modeled as a chemical change. Population decline. A population of animals or humans can decrease over time due to various factors like disease, predation, or any other factor. Machine failure. Machine or an equipment can deteriorate over time, leading to failure. And the last one, chemical degradation. The chemicals can break down or degrade over time due to reactions or some environmental factors. The most common example of this chemical degradation being the rusting of all the iron products, the products which are made up of iron. They get rusted over a period of time due to its continuous contact with oxygen. So this change is a chemical change, it can't be reversed back. But as regards or as far as this topic of pure death process is concerned, radioactive decay is the decay which can help us the most to model the pure death process. So in order to model pure death process by using radioactive decay, the concept of radioactive decay as an instrument, first we need to know what is a radioactive decay. So, in order to concise this vast concept of radioactive decay, I would like to show you this animation which shows the actual process of radioactive decay.
Reaction in nuclear fission. When slow neutrons are bombarded on uranium, each uranium nucleus is broken into two almost equal parts, and along with it, enormous energy and two or three trash neutrons are emitted. If the conditions are favorable, these neutrons take part in the fission. This leads to a chain of nuclear fissions, which continues till the whole of the uranium is consumed. The energy produced keep on multiplying.
So in case if the video was not as much clear to you in the first play, I would replay it.
Reaction in nuclear fission. When slow neutrons are bombarded on uranium, each uranium nucleus is broken into two almost equal parts, and along with it, enormous energy and two or three trash neutrons are emitted. If the conditions are favorable, these neutrons take part in the fission. This leads to a chain of nuclear fissions, which continues till the whole of the uranium is consumed. The energy produced keep on multiplying.
Okay, so after having seen this animation on how the decay occurs, if I am supposed to describe this observed process in minimum possible words and more by using flowchart, so I can get the following rough framework of this entire process. Here there is a neutron which gets bombarded on a uranium atom. Further, there is a release of two neutrons. There is a decay, and this decay continues till whole of the uranium gets decayed completely. So now this is a case of the radioactive decay. Radioactive decay in itself is a specific topic. But if I am supposed to form a chart on the same anvils on the same principle for any general process, so what can be a rough structure of any process of this form where there is a decay and there is no addition or no arrival? So it can be as follows. So this is a generalized form of this pure death process where we start from the first state, that is state 1. This is the state from which we start the process. Then we go to state 2, state 3, state 4 and so on till the concerned substance decays down completely. So here the time interval which is required for the transition, which is more specifically a decay or a death or a decrease, it is described in the terms of the rate of decay. Rather, now here there creeps some part of mathematics. So if the rate of decay is mu per unit time, then the probability of change in small time interval del t is mu del t. And if in case the population of the sample in state 1 is n, so the probability that death occurs in the population of size n is n mu del t, since there is multiplication of all the factors. So after having dealt with this rough and a very sketchy concept of pure death process, since we are supposed to see many things in the upcoming slide, these are few observations, few very rough and very crude observations which we can get. The first thing, the first two prominent points which stand out from the pure death process are that the birth rate is zero. That is, there is no addition of any element into this process, and the death rate is non-zero. That is, at every stage, at every instant, some or the other thing is going to get detached, or there is going to be some loss for certain. Now the element which needs to be understood very well in the context of this pure death process is of time, because the primary dimension which acts as a measuring scale for this process is not significantly of space but of time. Since the decay it can't be described with respect to the three dimensions of space. Rather, the decay can be efficiently described in terms of time. Thus, it can be successfully and logically said that the death or decay is a function of time. If there needs to be a graphical description of pure death process, it is to be done along the axis of time with second, which is the SI unit of time, as the unit of the scale. Now here, the intention behind the mathematical description of the pure death process is to describe the functional relationship between amount of substance decayed or otherwise the amount of substance remaining at a certain point of time. And with the general form of this mathematical function as the amount of substance decayed or the amount of substance remaining at a particular instant of time is the function of time. So with these crude observations, we proceed ahead. So we come to know about these theoretical properties of pure death process. The first one being the property of memorylessness. The process is memoryless, meaning that the future state of the process or the future outcome of any process depends upon only the current state or current population size and not on how it arrived at that state, which means that the the future of that process is going to get determined only by the present state. The occurrences which have took place so far does not matter, that is, it has no memory. The second property being current state dependence, which is somewhere synonymous to the first property. The transition rate, that is the death rate, depend only on the current state and not on any past state. Third being time homogeneity. The transition rate or the rate of death is constant over time, making the process time homogeneous. So now, if we take a bit of digression and we look upon the properties of Markovian process, so we will find that these three properties are also the properties of Markovian process. Thus, it can be said that a pure death process can also be considered as a Markovian process, and thus a pure death process can be analyzed and can also be modeled using the Markov chain theory. So now, after having dealt with this theoretical portion of pure death process, we have to also deal with this aspect of how pure death process can be described as a queue. But before describing pure death process as a queue, we need to know what is the general format of a queue. So as per the nomenclature of queue, it is based on a notation system which is developed by David G. Kendall in the 1950s. So the notation system is known as the Kendall notation. The general format is A slash B slash C slash D slash E, where these symbols have these meanings. A is the arrival process, B is the service time distribution, C is the number of servers, D is the capacity of the system, that is the elements in the sample at the beginning of that pure death process, and E being the service discipline, that is the way in which that system becomes functional or that mechanism becomes functional. So now, as far as pure death process is concerned, so it can be represented in the form of Q as m slash m slash infinity slash n, where m denotes the memoryless or Markovian service time distribution. There is no A, since there is no scope of any arrival, that is the sheer meaning of pure death process. So we haven't included it. Second M stands for Markovian arrival process, which is not applicable here, but there are some rules of description of Q which need to be adhered. That's why we have just mentioned it for the namesake. Third slash or third element is infinity, which denotes that the number of elements which can be at the beginning of pure death process are infinite, there is no limit. And last n denotes the finite population size or the initial population size. So the representation of this form summarizes the characteristics of the given queue. That is, we need not to write an essay to describe the characteristic of any queue. which is exercising the pure death process, this symbolization is sufficient to concisely describe all the characteristics. So now, after dealing with such a vast and such a intricate preamble, we come to this standard mathematical definition of pure depth process. How can pure depth process be described in a mathematical form? So, a pure depth process is a continuous time Markov chain, where the Markov chain is defined as xt, where t is always going to be greater than or equal to 0, that takes the value xt takes the value in the set 0, 1, 2, and so on till infinity, and also it satisfies the following properties. State space state space is 0, 1, 2, and so on up till infinity, where xt represents the number of individuals in the population at that particular instant of time t. Second property being the transition rate. The rate of transition is given by lambda n to n minus 1 equal to mu n, and lambda nm is equal to 0, where n is not equal to n minus 1 and m is greater than n. So firstly we need to know what is lambda n to n minus 1. So lambda n to n minus 1 is the transition rate from state n to n minus 1, that is to a state which is from n to n minus 1, it is equal to mu n, and lambda nm is equal to 0 for m which is greater than n. That is, the process can't go back. As I have said in very few initial slides of this presentation, this pure death process happens to be essentially irreversible process, so there is no probability of going back, thus it is 0. And the third property describing the initial condition is x0 equals to n, that is, the initial population is n since the time t is 0. Now, after having dealt with this definition of pure death process, now slowly and gradually the part of mathematics starts coming into our way. So we need to know how pure death process can be expressed in a mathematical form. So as I have said in the slide of the very few crude observations of pure death process, that the scale of measurement of pure death process is time, and time in itself is continuous in nature and is not discrete. That is, within every second there are milliseconds, within every milliseconds there are microseconds, and so on. Thus we can say that t tends to 0. And with this being the fact, it also implies that the interval of time can be infinitesimally small. It can be as small as possible, and thus there can arise certain situations where a time frame might have to be differentiated to make the intervals very very small, or otherwise many small time intervals have to be integrated to make them considerably and sufficiently large. Thus it implies the usage of calculus, specifically differentiation and integration, as an appropriate mathematical tool to describe the pure death process. So now, as we have dealt with the theoretical definition, the standard theoretical definition, although it had some element of mathematics, we need to express somehow this pure death process in the form of differential equations as well. Since the language of nature, it happens to be essentially and necessarily mathematical in its nature. So we need to express this pure death process in a mathematical form so that it becomes easy and convenient for further operations. So as we start with our first mathematical expression in this presentation, so before I actually dive into this juggernaut of substituting and resubstituting and deriving and so on, I would like to make few declarations. The first declaration being that while I would be deriving the mathematical laws or mathematical proofs, my intention by any means or by any way will not be to unnecessarily stretch the derivation or to unnecessarily do the things in 4 steps which can be reasonably done in 2 or even less number of steps. Rather, my intention or my purpose for that matter would be that while I move from one step to other step or from preceding step to succeeding step in the course of this mathematical derivation, the reason why we are succeeding from one step to another step should be clear for every step, so that once this flow of reason is clear to you, there is no need to literally cram all these derivations. This flow of reason itself will be sufficient for you to keep them in mind, and also it will help you to reinforce this mathematical rigor in you people as well, that is the audience. So with this declaration, now I come to the derivation. So there are few assumptions. The first assumption being that the population size at time t is nt. The death rate is constant. It is denoted by mu. The probability that an individual dies in a small time interval del t is mu del t, and pnt is the probability that there are n individuals remaining at time t. So we consider a small time interval del t. We want to find the probability that there are n elements remaining after time interval t plus del t. So we try to write this probability Pnt plus del t in terms of Pnt and Pn plus 1t as follows. So we have this Pnt plus del t equals to Pnt in bracket 1 minus mu del t plus Pn plus 1t multiplied by mu multiplied by n plus 1 del t. So I have colored, or I have tried to write each term or each element of this mathematical equation in different colors, different font colors, so that you can understand what is the unique meaning of each term and how each term of that parent equation further expands in the course of the mathematical derivation. So this Pnt 1 minus mu del t, it is the probability that no individuals die during the interval del t. So the number of individuals remain the same. And Pn plus 1t mu n plus 1 del t is the probability that one individual dies during the interval del t. So the number of individuals naturally decrease by 1. So simplifying the expression Pn t plus del t, we first begin with the equation which we derived on the previous slide, and now we open this red colored bracket, we multiply Pnt by 1 and by mu del t, and we shift the Pnt to the LHS, that is the left hand side of the equation. Further we divide both the sides by del t, and we take limit del t tends to 0 on both the sides. So we come to this stage. Now if we look at the left hand side of this equation, this resembles the definition of derivative, which you might have studied somewhere in the elementary portion of calculus. And as far as the RHS is concerned, so we take the del t common from the numerator. This del t gets cancelled from the denominator, and thus this limit on the RHS becomes irrelevant. So we get dPnt upon dt is equals to minus mu nPnt plus mu n plus 1 Pn plus 1t. So this is the differential equation for pure depth process. It signifies the rate of change of the probability of having exactly n individuals remaining at time t due to deaths or due to decay. So after having dealt with this expression of pure depth process in a mathematical form or in the form of differential equation, we need to know, or we need to study some very general statements which seem to have some functional importance in real life application of this process. So one of the very famous statement of this pure depth process is the theorem of the distribution of departure. So again, as I have said, firstly we will be dealing with the statement. We will see as to what is the message which the statement of this theorem is trying to convey, and further we will be trying to prove that message or to prove that particular assertion by using the tools of mathematics. So this statement says that assume that there are n elements in the system at time t equals to 0. Also assume that no arrivals can occur, which is yes, but of course, since it's a pure depth process. Departures can occur at the rate of mu per unit time, that is the output rate is mu. And with this being the given situation, P and T, that is the probability that n elements are remaining after time t has elapsed, is given by, now here there are two bifurcations or two disseminations for n, that is the number of elements remaining, being positive, and for n, that is number of elements remaining, being 0. That is, the expression is different in case the number of elements remaining are positive, and is different in case there are no elements remaining after that particular decay process has occurred. So here are those two expressions, and now we need to prove them. So we will be heading towards our proof, and the declarations which I made while deriving the differential equation, with the same intentions I will be dealing with the proof of this theorem of distribution of departure as well. So here is the proof. So we first look as to what is given to us. So there are capital N elements in the system at time t equals to 0, and no arrivals occur. Departures can occur at the rate of mu per unit time, that is the output rate is mu, and the distribution of departures can be derived on the basis of the following three axioms. Axioms here in the language of mathematics refer to some results which are very much obvious in their nature, that is, they don't require any formal proof. So the first axiom being that the probability of one departure during time interval del t is mu del t. The probability of more than one departure during time interval del t is considered to be 0, since the time interval is so small that the probability of more than one elements to depart during this time is nearly 0, and can be considered negligible to avoid further mathematical complications. Thirdly, the third axiom being that the number of departures in non-overlapping time intervals are statistically independent. That is, in two separate time intervals, the departures which occur will not uh, demotivate or otherwise motivate the occurrence of each other. So after having dealt with these three axioms, we have P and T, which is the probability that n elements remain after time t has elapsed, and the distribution of departures, which is the aim of this theorem, will be defined in terms of this P and T, as we have seen in the statement of this theorem. So for proving this theorem of departures, there are following cases of combinations of the initial number of elements in the system, that is capital N, and the number of elements which are remaining after the process has occurred, that is small n. So first case is the one where the capital N and small n are equal, that is number of elements before system and number of elements after system are equal. Second being the fact that the number of elements remaining after system and the number of elements before the actual process occurred are not equal, which have further bifurcations, that there is only one departure and there are no departures. And third being the case where there are no elements remaining in the system, that is, all the elements of the system are used up in that particular process. So we will be making some derivations, or we will be reaching some milestones for each of these cases, and further we will be interlinking those cases to gradually move or to gradually proceed to our desired result. So here is the case 1, when the number of elements in the system, that is capital N, and number of elements remaining are not equal. So we deal with the first situation. So here one departure occurs in the time interval del t. So here it means that there should be n plus 1 units in the beginning, and after the time interval del t has elapsed, n units should remain. So thus there are two occurrences or two facts which are turning out to be true at the same time. The first being that there should be n plus 1 units before the process, and there should be one departure during that actual occurrence of the process. So in the probability theory, when two events occur together and we have to calculate the probability of the combined events of the two parts, so this necessarily implies that the probability of those two sub events needs to be multiplied. So here we multiply those probabilities. It is p n plus 1 t into mu del t, and we name this as equation 1. And we have second situation where no departure occurs in the time interval del t, which means that before the occurrence of process there are n units, and after the occurrence of process 2 n units remain. So again, on the same angles of the situation 1, we formulate the probability of those two combined events as p n t into 1 minus mu del t, and we name it as equation 2. So these two equations 1 and 2, these denote same process for two different cases. These are two different cases. In the first situation there is one departure, in second situation there is no departure. And in order to generalize them, we need to add the RHS of these two equations to get a general equation, which is as follows. So we get this general equation, which is named as equation A. Now we deal with the case 2, where small n equals capital N. So this means that probability of n plus 1 units to remain after time t has elapsed is 0. So we make this substitution in equation A to get Pn t plus del t equals to Pn t multiplied by 1 minus mu del t, which is equation B. Now case 3, when n is equals to 0, so mu also needs to be 0, since if there are no elements remaining, the decay rate has to be 0 thereafter. So from equation A, we get Pn t plus del t equals to P1t. Since n is equals to 0, so we get n plus 1 here as 0 plus 1, which is equal to 1. So P1t into mu del t plus P0t multiplied by 1 minus 0, which is as good as 1. Now, after dealing with these three equations, which are a positive milestone in this course of derivation, we do certain mathematical transformations for equation A, and we get that we first take this equation as it is, we expand this bracket, we shift that p and t to the LHS of the equation, we divide both the sides by del t, we take limit del t tends to 0, and by using the same logic as we used in the derivation for the differential equation of pure depth process, we get this equation which we name as equation 3. And similarly for this equation B, we perform the same mathematical treatment to get this equation 4. Now, after dealing with equation 3, we shift the p and t to the denominator of LHS, and it can be described by doing certain necessary mathematical adjustment as the derivative of log of p and t, which is equals to minus mu. And if we further integrate this equation, we get log of p n t, which is equals to minus mu t plus m, where m is the constant of integral. Now, this integration constant needs to be found out, and it can be found out by substituting the boundary conditions to get Pn0 equals to 1 And if p n 0 equals to 1, so m turns out to be 0. Since log of 1 is equals to 0, so m turns out to be equal to 0. And thus we get log of p n t equals to mu t. And we can come to this result where p n t equals e to the power minus mu t. Since we need to cancel this log, so we need to raise this minus mu t as the exponent of e. Now what we do is we substitute this n as n minus 1 in equation 4. So after doing this, we get this equation, and we shift this minus mu p n minus 1t to the LHS of the equation, and we get this differential equation, which can be solved by using the concept of integrating factor. So here, to solve this equation, we use integrating factor e to the power minus mu t to get this equation, and again by using the boundary conditions we solve it and generalize it to get this equation. Now this is somehow an equation which is not so much in rapport or attuned to the one which was in the statement of this theorem. So what we do is we do some necessary mathematical adjustments, of course, and we consider small n equal to capital N minus I. So I becomes capital N minus small n, and we get this expression for p n t, which is mu t to the power capital N minus small n e to the power minus mu t upon capital N minus small n factorial. This is the result for the number of elements remaining to be positive. Now we also have to derive the result for the number of elements remaining to be 0. So for that we consider the summation of the all the probabilities of number of elements remaining after certain time t has elapsed. And as we know that the sum of probabilities is 1, so this p0t equals 1 minus summation n equals to 1 to capital N. We take the limit of summation from 1 to capital N, since p0t is already on the LHS of this equation, and we apply the result which we have derived in this equation p to get this equation q, which gives the result for finding the probability that 0 elements have remained after time t. And this, after combining the equation p and q, which we get this result, and this is also called as the truncated Poisson law, and this is the statement which we were actually required to prove. So this is the required mathematical expression for the law of departures. So after having dealt with this part of, or rather rich part of mathematical treatment, which was so much intensive in its nature, we need to apply these results or these mathematical aids into some real life context. So in order to serve the same purpose, in order to exercise the same intention, I would like to uh, describe this real life problem. So here is an illustrative problem. A hospital emergency room has 10 beds. If the hospital is currently full, this very fact that the hospital is currently full, uh, of course, says that there is no scope of any more arrival of patients, which clearly signifies that it is a pure death process. And the output rate, that is the decay rate, is 1 by 3. So we have to find out that what is the probability that exactly 6 beds will be vacant after 2 hours. So time t is equals to 2, and here the thing which needs to be looked upon very well is that the number of beds, or in general the number of elements which will be vacant, is given, whereas the formulation which we have done, or the result which we have derived, is in terms of the number of elements remaining. So we have to do these comprehensions for ourselves, to get that the number of elements left after the required time elapsed, that is capital small n, will be 4. So with this data being synthesized, we take the formula, we plug all the values, and we do the necessary calculation. I have also included a screenshot to show as to how the calculation is done. So we get the probability as 0.0002375714. So we also come to know that the probability that exactly 6 beds will be vacant after 2 hours is 0.0002375714. Now this result, somehow this answer which we have found out, is not meant to be calculated and further forgot. I mean, it is not the case that we will just find out the answer by doing the necessary substitutions in the mechanical form and we will forget it. There are some relevant and there are some uh, solid results or solid messages which these digits give us. They are not benign in their nature. So what is the message which this probability is trying to give us? So it is saying that the probability that exactly 6 beds will be vacant after 2 hours is very, very, very less. So what it exactly means, that there needs to be some arrangement by which more beds are employed in order to avoid any ill-fated incident. So this somehow nudges us to know as to how is this concept of pure depth processes relevant in the real life disciplines. So here are a few of those examples. So firstly, to determine the battery life of the equipments, there are certain equipments which work on battery, and those equipments, they are many a times playing a significant role to keep someone alive, for that matter the equipments which are used in the hospital. So it is always better to know as to what is the probability that the equipments will survive or they will sustain for a considerable time, so that the necessary arrangements can be done beforehand. To determine the decline of a disease in case of a pandemic, so it can help us to know as to how long we are supposed to fight with a certain disease, so that the necessary arrangements of doctors and hospitals can be done. To determine at what rate a certain species of animal can turn extinct, so it is very essential as far as the proper upkeep of the ecosystem is concerned, so that necessary measures can be taken for the sanctuaries and the saving and ban on poaching and all such things can be done in order to maintain their numbers. To determine a decrease in population due to emigration over a certain place, so this can be used to determine the demographic changes or cultural uh, changes in the cultural dynamics of a certain country. And the last one being to determine the failure rate of computer network. So in this age of computers and all these sophisticated devices, so it is essential to know what is the failure rate of the computer network, or for that matter any mechanism network, so that it can be rectified within time. But after having dealt with this, there is a side note which states that no process is a pure depth process in the universal scale and context of time and place. A pure depth process is to be essentially defined over a specific period of time and for a specific place. That is, the decay, or for that matter this death of the animals, the endangered animals, is only a pure death process till the animals do not start uh, proliferating themselves once again. This this decay of battery, it is a pure death process only till it is not recharged once again. This decrease in population due to immigration is a pure death process only till there is no uh, incoming of people from the another countries back into the original country. So this needs to be known very well that pure death process is not a process, or for that matter, even pure birth process is not a process which is going to be defined for eternity. It is very much specific and is described in distinct terms of space and time. So after having dealt with this vast presentation, now it's time for me to end my few words on this topic. So it's the time for acknowledgements. So here are the resources which I used to design my seminar and to gather the content for my seminar. So I thank you for holding on with me for such a long time and for your attention and also for your precious time.